But we are, as I mentioned, then halfway through the class and ready to go on to magnetic fields. Although I didn't get a chance to do too many example calculations from the 28 here. And there are some little subtleties that I do want you to see. So I thought I better start class doing that and hopefully not do too many, although kind of balance it between a lot of examples and then getting on to our magnetism. So we'll see how far we get here today in terms of our magnetism. So turning to the end of chapter 28, as you already saw, I did probably one of the most straightforward examples was number 5, where we looked at the equivalent resistance. And if you recall that one, in fact, let me pull that back up from the chapter here, because the circuits that I want to do here is what I want you to see. And so we were working, and still are for that matter, on chapter 28. And projector would be helpful. Let that warm up. And we had done number 5. Maybe I'll shoot it back up there while it's warming up. But now that we've done 5, let's move to the second example I have here, number 17. So I'll put here number 17 on the board here, and I'll read it here in just a second. But it basically says, look at the circuit and determine the current in each resistor. And it could extend on and say, give me the current, give me the voltage, give me the power. All right? And so that's the one we did before, just to kind of jog your memory. That's 5. Scrolling down here to 17, here's what 17 looks like. And so it looks like there's 1, 2, 3, 4, 5 resistors here, and 2 batteries. And I think this might be the first time we've done 2 batteries, and that's why I grabbed it. Just wanted to convince you of, well, in lab I guess we did 2 batteries, so there was one that you guys did. Now number 6 in the lab, you had to do Kirchhoff's loop rule and Kirchhoff junction rule and find the current. And same thing here. That's what I just want to show you here today, and you're going to have a lot of homework this weekend on ones that might have 2 or 3 batteries in them. And they have a big effect. They have an effect in the sense that the voltage would be different on one side of the battery or the not, which would clearly then change our circuit and make it a very good chance that it is not series or parallel. Because when you separate it in 2 branches like this, I think you can quickly see that this branch and this branch are not in series. They separate it off. They kind of look like they're parallel. And in terms of the whole branch, I would say yes, they are in parallel. But I would in no way say that that resistor is parallel to this resistor. Even if you notice that these 2 are in series and you put them together, you would still not say that resistor and that resistor are in parallel. Even if you combine that one with that one, you still wouldn't say that, because you would have a change of voltage due to the battery. So again, this is a good example of one that is not series and not parallel. So we won't try to do this with the equivalent because of those batteries in there. But also it's a good one to show you that I can do part of it with the equivalents. And I think that would simplify a few steps. So this is the whole circuit. The question says find the current in each resistor. And maybe in the interest of time, I won't solve the other part. But if we knew the current, could you get the voltage in each resistor? Right? Current times the resistance would give you the voltage. Okay, fair enough. And then if they asked for the power in each resistor, could you get that too? Would it just be current times the voltage now that you've done those? Or you could go current squared times resistance. Or you could go voltage squared divided by resistance. Okay, so if we really get the current in each of them, which is what this problem is asking, then the ability to solve for anything else, I think, is a little more straightforward. But let's kind of simplify this a little bit. I would start off by saying, look, I have an 8 ohm resistor here. That's true. But as I look at what I might call the middle branch here, that 5 and the 1, as you look at those, can you kind of see that the current that is going this way? Maybe. Or the current that's going this way? Not sure. At this point, I don't know. Doesn't really matter yet. But whatever the current is, leaving this one, going into that one, or leaving this one, coming into that one, they're the same, aren't they? And so hopefully you see that these two are in series. And so maybe I would make this kind of first step here and say, okay, look at that middle branch for a moment. That middle branch is going to give me a 6 ohm resistor before it connects up to my 4-volt battery. So that might be kind of the first step as I look at this. Even if I don't recognize that, I'm not going to be able to go the whole distance of making the equivalent series and parallel. I would even say the same thing with this other branch. Take a look at this one. I mean, even though they're not in a straight line, they do have the same current that comes out of the 3 goes into the 1, right? There's no extra wire along the way. There's no place for the current to go but into the next one. So if the current flows, and probably since this is the strongest battery in here, I am going to take a reasonable guess here. Could be wrong. I doubt it. It seems like a good, solid guess that the current is going this way, and it is the stronger battery here, and it's going to push it like that. And so whatever current comes out of this number 1 ohm resistor goes into that number 3. It has no other places to go. So again, I would say those are in series with each other. And so that makes the other side of here, what was over there, a 3 and a 1, for a total of 4 ohms. So this would be the equivalent circuit of that, realizing that 2 pairs are in series. And I can make it now a little bit simpler. But this is where I would get stuck if I tried to say, are any of these in series and in parallel? And you can kind of see that no, I mean, clearly they're not in series, because to be in series, the current from this one would have to go and not have a junction. It would have to go right into that one. So this one and this one are not in series because of that junction. And as this comes up, it's going to split. Okay, so it can't be in series with those. So none of these 3 remaining resistors are in series. And likewise, none of them are in parallel.
Could you do a Norton-Devlin equivalent?
Could you? Yes. Will we? No. We'll wait until you go to a circuits class before we do the equivalent of that. So, and just by you saying that, and actually you telling me before, I know you're in the circuits class. So that's, that's the next step, and that's what the circuits class is for. All right. So we're not going to go that far. We don't need to go that far. We could just write out our conservation of energy, our conservation of charge, put in our matrix, and solve it. Okay? And that's what I'm going to do. But again, just as a good example to show you that, look, when you have a circuit, you need to look at it and say, are they in series? Are they in parallel? Or are they neither? Okay? And take advantage whichever technique works best for you. The equivalent circuit is the first technique we learned. If that doesn't work for you, we go back to basics with conservation of energy and conservation of charge. As you go further in your education into your circuits classes, you'll do things like mesh current, node voltage, and Devlin, and all those good things.
Are we allowed to do stuff in circuits on the test?
Sure, okay. Sure. I have no problem with that. I'll read it. What am I trying to say is just be careful, because I've seen students who think, I'll just do this equivalency, and it's really not equivalent for this one, and I'm really going to type bind, okay, how am I going to grade this one? Because it's so different, and I'm not real sure where they fouled up because they didn't do much work, but anyway, it's just don't foul up, and it'll be 100% right, it'll be easy for me to grade, I'll just put 20 out of 20 and move to the next one. Yeah. All right, so like I said, part of this I wanted to show you was that I can have a mix and match within my circuit. The equivalent resistance is partly done, but now I'm kind of stuck. Now I'm going to go back to Kirchhoff's loop rules here. I'm going to label some things. I'm going to label some current on here first. And again, maybe putting the plus and minus to kind of remind myself that the longer leg is for the positive. Pick a direction of the current. And again, Just wanted to remind you, you're really picking a direction. You're not saying for sure which direction the current is, but if we work out the math and we get a negative number for one of our currents, that tells us really we are going the wrong direction, okay? And so that's really what we mean. Personally, we had a little discussion about this last time on how you want to set it up, but my approach is to make a reasonable, educated guess on what direction they flow, realizing that I don't have to be completely right. Just if they all come out to be positive, I happen to get it right, and I like to think of things in positive. So I like to step back and look a little bit at the physics. And in this case, as I was saying, I would look at this one and I would say, let's call the current that is from this battery number 1, and let's say it's going in that direction. Now I think that's a reasonable guess, a very strong guess, because as I will look, this one here, of course, is fighting it, right? And so that's why you may say, you know, I'm not 100% sure the current goes that way. However, I would argue that, isn't this one stronger than that one? And so they're going to compete with each other, true, but this one seems to be stronger than that one. Although, again, that's not a complete answer, because the current does lose some of its energy as it goes through here. And so there's going to be a change here. And then it comes up and it splits. And so I'm not sure you can exactly argue for sure without doing some numbers here. But this one's pretty solid. This one is, hey, strong battery here. Yeah, you're going to lose some voltage here, but you're going to lose some here too. Okay? And since this is actually at a lower resistance, all the more reason I think I'm going to lose less here. And so if this drops a couple of volts, this one probably drops even more. Unless, of course, there's less current. But now if there's less current, then this one would win. So all of that says, you know, I haven't done the numbers, but I'm 99.99% sure that's the direction of that one. But again, you probably don't even want to take that long to analyze it. Really just pick a direction, go through the math, and see if it comes out negative. But I always start with the stronger one. All right, so there it is. And now, for that matter, this is pretty clear to my mind too, that this, which I'll call number 3 over here, that, look, the current here, when it comes out, if it is coming out of this battery, is going to merge up and go that way. I don't think this is going to override it and go this way. It is possible, though, that this current comes here and overrides this one and goes that direction. So this part of it, I'm not 100% sure which way the current is going. But I'm pretty confident that on this outside part, it goes in that direction. But again, maybe I'm spending too much time here because I want to emphasize, it doesn't really matter. Pick a direction. That's the definition of positive. Write out the equations, solve the math. If you get a negative number, it's in the opposite direction. But I'm pretty confident with the 1 and the 3. It's the one in the middle that I have less certainty with it. I'm looking at this saying, all right, this gets weakened as it goes over here. And if it gets weakened so much that the voltage drops less than 4 here, then it's possible that this guy then has enough volt 4 that is going to push over to here. But that would have to give me a lot of current. And since this resistor really is more than that one as it goes around here, even though they're not the same current, I'm kind of thinking that this is going to have more voltage than that. So I don't think this is going to be able to drop to even half as much. And that means that's going to really be at 6 or higher. And if that's 6 or higher, then it can push against that 4 really easily. So all of that said, I'm pretty sure that what's going to happen is it's going to go that way. But that's the one then I would just say, hey, don't even think about that one. Pick a direction, write out the equation. And what might bother you, and the reason I picked this one is, isn't that opposite to the way the battery wants to make the current go? Can the current go opposite to the direction the battery wants it? Sure, if something else is pushing it that way, right? I mean, this pin wants to fall because of gravity. Does that mean it can't go up? No, it could go up. It could go up if I push more than Gravity, right? I can make the pin go up. So the current could go the opposite way. It all really depends on how much this one is pushing by the time its voltage has been dropped as it goes across that resistor. And like I said, I'm thinking because this resistor is bigger than that one, there will be a drop, but it won't even be 6 volts. And because of that, this one, even if it dropped to 6 volts, would still have more power than that one, and it would go this way. So the current's going in the opposite direction. So that was one of many reasons I picked this problem. I wanted you to see the current could go the opposite direction when you have the 2 batteries in here. In fact, how would you describe what was going on to that 4-volt battery then? It's being charged, right? This is what you probably do every other day. You take out your cell phone, you take out your iPod, you hook it up to some kind of charging device, and you use a stronger power supply to force current the opposite direction and to undo those chemical reactions and to recharge that battery so that later on you can take it off. So in a sense, we're using this 12-volt battery here to charge up this 4-volt battery. So that's really what we have going on here. I think. I could be wrong here. We'll see what the signs come out for my current. Yeah.
Is that problem assuming that there's no internal resistance? Because if it was like a 12-volt bit battery, couldn't the 4-volt?
Oh, yeah. Okay, fair enough. Now, as you're pointing out here, this does not show any internal resistance, right? So it's either A, assuming these are really good batteries, new batteries with no internal resistance, or if you look closely, I would wonder if the author isn't really saying this is the battery, right? Where the battery is made out of the EMF and the internal resistor. And that's where this 1 comes in. And then the 5 is external in part of your charging electronics so that we don't shove too much current through it at one time. And I can't help but wonder if that's not the logic going on in the author's mind too. So you're right, he doesn't say anything about internal resistance directly, but I think the circuit is battery, external resistor. Just reading into that small 1 ohm resistor is what he puts there. So I would say he is including an internal resistance. It's included already in here and in here. Okay, but now we get to our Kirchhoff's rules that we learned. Let's start with the number 1. Let's start with the junction. You can kind of see that it says the current going into a junction is equal to the current coming out of a junction. So the way I've labeled this is the current going in is number 1. So there's the current going in. And that equals current 2 and current 3, right? So that would be equation number 1. Oh, and I told myself I'd do it in the other order. I'd do number 2 first. Because remember, we need how many equations to solve this? 3, right? Because we have 3 unknowns, current 1, 2, and 3. Okay? And I think it's easier to find your independent equations if you start with the second one, the loops. Because how many independent equations can I get from the loops? Do you see that? I mean, how many loops do you see up here? Do you see 3? You see a left loop, a right loop, and a big loop. Now the big loop is really nothing more than the combination of the left and the right. So the big one is really not an independent equation if you've already done the left and the right. Fair enough? Or if you've done the big one and the right one, isn't the left one the big one minus the right one? Gives you the left one? So if you do the big one and the right one, you're not going to want to do the left one, because that left one would be a linear combination of the other 2. And likewise, if you do the big one and the right one, then you don't want, left one, you don't want to do the right one, because then the right one is nothing more than the big one minus the left one. Fair enough? And so to help you find enough equations, I like to start there with the loops. And as I said last time, look at the little loops, because any other loop is a linear combination of the little loop. So you can see how many independent equations you get from the loops right away, and then you can go to your nodes and get the rest of them from the nodes. And so had I started there, I would have said, I'm going to get 2 equations from my loops. I need 3, so I must get 1 from the nodes. And you can see there's a node there. There's a node there too, but I'm thinking you can see how these two come together. This node is really the same as that node. It's not a new piece of information. So that's kind of the easiest way for me anyway, is to find out how many independent equations can I get from the node by first looking at how many can I get from the loops. Okay? Because like I said, if you just stop and go, oh, I need 3 equations, and you do 3 loops, you're not going to be able to solve this because you don't have 3 independent equations. So left loop, right loop, and top node would be a good place to go with this. And like I said, if you do nothing else, maybe just do the small loops. And so I'll do the small loops. Maybe I'll start down here and do a left loop. If I start down here and write an equation, I would go from here to here. That is clearly a change of voltage of 4. The question is it a plus or a minus change? Here, going to here. Here, going to here. Is it a plus or a minus? Okay, and it's positive. Why?
Against the current.
It has nothing to do with the direction of the current. When does the direction of the current matter? For the resistors, exactly. So again, be careful. The change in voltage, plus and minus, is determined by that little line or big line. It's determined by the chemicals inside. So this is a positive change in 4. Okay? The voltage, plus or minus, on a resistor has to do with the direction of the current. And the voltage, plus or minus, on a capacitor has to do with whether you have a positive or a negative charge on that plate. And those were the 3 elements we've been working with. The batteries, the resistors, and the capacitors. All right? So this is a plus 4 because I go from little line to big line, not because I go against the current. With that said, then when I go through my circuit and I change my voltage by 6I2, is it a plus or a minus? Is it an increase or a decrease? Answer? It's an increase. Why? I'm going against the current, right? I'm hiking in the creek, splash, 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 and I know if I hike against the flow of the water, I know I'm going uphill. I'm going to higher energies in that case, gravitational potential energy, but in this case, of where it's coming from. The whole reason the current is going this way to this way, the whole reason the water is going from a higher to a lower is because from one side to another, is because it is higher energy down to lower energy. So continuing my little imaginary hike through the wire, I get to this one, which would be a change of 8I3. And 8I3 would be a change plus or minus? Minus because? Yeah, I'm going with the current. Okay? And so there would be my loop on the left. And if I do the loop on the right, oh, I'm really tempted to do the big one. What do you want me to do? The right or the big? I better do the right one since I said I would. But 1, 2, 3, 4, I got to do 4 things. If I do the big one, I only have to do 3. But I said I would do the right one. So all right, let's do the right one. So I have my 2 equations. And so let me start here. Let me go for this little imaginary hike. Starting here, going this way. I go from minus to plus. Right? There's a change of 12. Little line to big line. Okay? I don't care what direction the current's going. In this case, I happen to be going with the current, but it's not a resistor, so I'm not going to put a negative there. I'm going from little line to big line. Okay, so there's a change of 12. Now here would be a change of 4I1, and then I have to ask myself, is it an increase or is it a decrease? And I'm going with the current. And again, if you're hiking in a creek going with the current, you are definitely going downhill. So this is a decrease in voltage. As I continue on and I make this little cut and come through here, again, there's a change of 6I2. I'm going with the current again, so that would be a negative. I then get to this second battery, the one that we're charging here probably, and it is a change of 4. That's just given. That's the voltage on the battery. But is it an increase or a decrease? Yeah, it's a decrease. Good. I know that right away because I am going from the big line to the small line. I am going from higher energy down to lower energy. That's what the line means. And that completes the loop. So the total changes in voltage as I go around the loop is now 0. And so there's my 3 equations, 3 unknowns. And as I showed you once, but thought I would show you a second time, and I actually learned something too, so this last couple of days, but there is a nice little program, yay, that allows you to emulate the calculator here. So instead of me trying to hold it up and do the matrix, let's actually do it live here on front of the screen here. But this is a perfect one to put into a matrix. It's a 3 equations, 3 unknowns. You can solve it anywhere you want. If you want to do Kramer's rule, you can. If you want to do elimination method, you can. If you want to use substitutions, you can. I'm just encouraging you to do the reduced row echelon form and use the power of your calculator. 3 unknowns isn't quite so bad. 2 unknowns, it's probably not worth even getting the calculator out. That you should probably just solve with math. 3 is kind of that transition. 4, definitely just get out the calculator. 4 equations, 4 unknowns, But in this case, yeah, we could probably, actually elimination would probably work really well here. And even substitution with this one. But instead of doing all the math, let's put it into a matrix. So let's write this in its matrix form. I guess I would write this as the first equation as a 1, negative 1, negative 1. I1, I2, I3. Then equals 0. So that is what this first equation is saying, right? When I move all of my unknowns to one side, I get I1 minus I2 minus I3 equals 0. So that's equation number 1. Equation number 2, it looks like my unknowns are a 2 and a 3. So I've got 0 I1, I've got 6 I2, I've got minus 8 I3 equals, and I'm going to bring the 4 to the other side, so that's a negative 4. So there is my second equation written in a matrix form. 0 I1, 6 I2, minus 8 I3 all equals negative 4. And then finally this last equation has a negative 4 I1, has a negative 6 I2, has a 0 I3, it's not even in there. And when I put the negative 4 and the 12 together, that's an 8, bring it to the other side, that equals a negative 8, right? And so now I can enter this matrix. Well, let me actually just enter it, not write it out. But this would be a nice 3 by 4 matrix, where this is the 3 by 3 with this tagged along. And after my calculator does a little bit of work, it will diagonalize the matrix through a long process of manipulating this matrix around. But of course, what it does to one side, it will do to the other. But that's really then going to be the answer. Once I get a diagonalized matrix, it is saying I1 is that, I2 is that, I3 is that. And that's why this form is kind of nice. So coming over here to the TI-83, let's see if I can use this. I will turn it on. I guess I got to do that first. Okay. Go to the matrix menu, and I will go to edit menu, and I will edit matrix A. Hey, this is fun. Okay, so I'm going to put in that matrix. It's a 3 by 4 matrix here. So I will put in the 3, enter, by 4, enter. And looking at that matrix, across the first row, I've got a 1. 1. Maybe I gotta click the button here. Oh. Yeah, hang on. Let's see, how do I... Arrow, delete. Hoo-hoo, all right. Yay, all right. -1, enter. -1, enter. 0, enter. Yay, there's the first row. All right, yeah, that was kind of cool. Even though it's the same button, it's a little different using the mouse than you're using your fingers. All right. Okay, and then the second row is a 0. I guess it's already a 0. A 6. Did I see a -8? Yep. And then what's the next one?
-4.
-4. Tempted to do some multiplication by -1s to get rid of so many negatives in there. Okay. -4 on that one? -4, enter. -6, enter. 0, enter. -8. Thank you. All right, so I have now entered my 3 by 4 matrix. And obviously what I'm trying to say in all this is learn to use your calculator. This is the 83. I thought if we called it up it would help you learn it, but it's really nice obviously to get 4 unknowns out of this, 3 even, 2 maybe not so much, but here is your matrix. So then, if I guess I kind of quit that for a moment, what do I want to do? Well, I want to take the math of it. I want to scroll down till I get to the reduced row echelon form, and there it is, of matrix A. So I'll go to matrix A. And if I hit enter, it will go through all the math for me. And so there you have it. The calculator has done whatever it needs to multiply by in order to diagonalize this. But of course, if you do it to one side, you have to do it to the other, and then the other side then is the answer. So I can scroll over and get my currents. I will give you a little bit of a warning. I have unfortunately made this mistake, and I hope you don't. But it says, in fact, maybe I should just show you what the screen looked like before I scrolled over. I mean, when I look at this, I see 1.3, right? And so I'm tempted to say current number 1 is 1.3, and I agree. But I've had it'd say 1.3 times 10 to the -3. Right? And unless you scroll over, you may not see that times 10 to the -3. So I would encourage you to scroll over and see if your calculator is not giving it to you in scientific notation. It doesn't look like that one came out to any kind of scientific notation, but scroll all the way over. So this would tell me current number 1 is 1.3, and then current number 2 is 0.46, and that's the one I was kind of curious. Positive number or negative number? Yeah, number 2 is positive. What does it tell me?
You were right.
Yeah, my guess was right, or in other words, it tells me which way it was down, and so this is down. And again, don't want to make a big deal of whether you were right or wrong. That's not important. What's important at the end of the problem, do you know how much current you have and what direction it is flowing? So in my case, I got all positive numbers, so my initial guesses are correct, and those are the numbers that it comes out to be. Yeah.
If we do come out with a negative number, should we actually flip it on the graph, or should we leave it the way it was before so that the math makes sense?
I would say couple it with what you are going to, if this is a test, couple it with what you're going to put down in box. So in other words, if you're at the end of the problem, if you're going to give me a positive number for the current, then in the diagram you have, make sure the arrow is in the direction that means positive. Does that kind of make sense? So that your diagram matches your sign at the end. Okay? put another way, you don't need to change anything. If you have label it one way, you get all the way to the end, and you say the current I2 is a negative 0.4. I'm good with that, because what I'm going to do is I'm going to look at that answer and say, okay, that's a negative 0.4, meaning the magnitude's right. And then I'll look up at your diagram for your direction, and I'll say, okay, negative means opposite of the arrow he has up here, and so make sure they match. But I don't care if you go back and change it. That's, yeah. A personal choice for me is I would go back and I would change my negative to a positive, and I'd go back to my diagram and change the direction. But then again, that might actually confuse me, the grader, as I look at it, saying, well, he's got an arrow. Now that I think about it, he's got an arrow one way, but when he first writes out his equations, it was corresponding to the other way, and he changed it at the end. So, I mean, hopefully I would notice that, but obviously you don't want the grader to get confused. Yeah. Well, anyways, that's one of them, and that I think was a worthwhile one looking at it. And some of these other ones get a little more sophisticated and a little bit more complicated, if you will. But again, they all follow the same basic layout here. How about if I try 29? Now, 29, they don't list a circuit here. They just kind of describe it. But I grabbed it because it has a capacitor. And that was kind of the last thing we did in the chapter. We worked with a capacitor. Now, the one after this will have both capacitors and resistors. But this one has a fairly simple circuit comparatively speaking. It says here a 2 nanofarad capacitor is initially charged to 5.1 microcoulombs and is now going to be discharged through a 1.3 kiloohm resistor. So we have this where we say, okay, here is our capacitor. It has some initial charge, I'll call it Q naught. 5.1 microcoulombs is the value. And they are going to then take this and discharge it, that is, hook a wire to it and kind of get the charge off of it. Maybe we are disassembling something and we want to work with it, we want to repair it. And this capacitor has a lot of stored energy in it, so we want to make sure that it's, energy's gone before we start handling it and shock ourselves here. So we're going to hook up a couple of connectors with this resistor and discharge it. And that's what the problem is saying here is A, calculate the current through this resistor after 9 microseconds. Let's see if I read this right. Calculate the current in the resistor 9 microseconds after the resistor is connected across the terminals of the capacitor. B, what charge remains on the capacitor after 8 microseconds? And C, what is the maximum current in the resistor? Okay. Now, we worked this out, and I can do it again if you want. Do you remember what this came out to be? Do you remember how we did the loop here? And we said, okay, if this starts as positive, and I go from here to here, that's Q over C. That would have to equal to, and then minus IR would have to be 0. That would be our loop. And then we solved this. We said the change in the current on the capacitor would be equal but opposite to the change of the charge going through the resistor. And then so this here, taking negative of the derivative of the charge on the capacitor, is actually the derivative of the charge through the resistor, which is the current, blah, 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 blah. Do you remember what we got? Does that look familiar? Okay. Should I do the math again or no? Okay. All right, so there is what we came up with last time as it discharges. And so once we know that, it's a pretty straightforward problem now because we do know it's discharging. The charge is going down according to this. And it asked a couple of questions. It did say in A, calculate the current. B, what charge remains on the capacitor? Well, maybe I should do B first. B is saying calculate how much charge is on that capacitor after 8, let me just double check that, after 8 microseconds. So this one is going to be, all right, I'm starting with 5.0 microcoulombs times e to the negative, and there's the time, 8 microseconds over, and then this is what I wanted to remind you of. What was this tau? What was this time constant? RC. Yeah, RC. So we often call it the RC time constant. Okay, and so that would be the resistance. Now I do want to point out, especially as we get to the next problem, what resistance is it? Which kind of a silly question for this one. There's only one resistor up there. But that could change real quick. But remember, the resistance is what it is discharging through. So in this case, it's 1,300 ohms. They did say the capacitance at the beginning, I didn't put it at the chart here, but they said this was a 2 nanofarad capacitor. So this downstairs becomes 1,300 ohms multiplied by 2 times 10 to the minus 9th. And that should give me my charge. Oh, I can use this calculator. Probably take a little longer. Yeah, probably not worth it. All right, so I just wanted to do that one for the matrix and show. So in the exponent, I have 8 times 10 to the negative 6 divided by 1,300 divided by 2 times 10 to the minus 9. And now if I go e with a negative of that answer and then multiply by the 5.1 that I start with, I get a 0.235 microcoulombs. Okay. And so I think that's the easier one of it, and really not the main reason I picked it, although I did because I wanted you just to kind of mentally review our decaying or our discharging capacitor and that time constant. But the part I want to add to this is the part I didn't get a chance to show you in the lecture here was, okay, could you give me the current from this? Because that's really what A is saying, right? A is saying, calculate the current in the resistor 9 microseconds after you make the connection. So how are you going to get current? Yeah, current in the resistor is dq dt, right? It is how the current is changing, which we said when we solved this problem is negative of how the charge on the capacitor is changing. That's where we got the whole idea of the current in the first place. That the stuff that came off of the capacitor went into the resistor. All right? So let me take the derivative of the charge on the capacitor. The charge on the capacitor is what we worked out here. So this would be a Q naught e to the minus t over tau. And so as I take this derivative, the Q naught is unchanged. The derivative of an exponent or exponential is still an exponential. With the chain rule, bringing down the negative 1 over tau. And then the two negatives cancel off, and I get the current flowing with a positive number, and a positive number is the direction that I chose as positive, and in this, I didn't put it here in the diagram, but as we derived this equation last time, that was how we set it up. So yeah, the current's going in the direction I thought it would go. Okay, come up with a positive number. That's not a big surprise here. Okay, and now I can put this number in. This is the 5.1 microcoulombs here. Downstairs is the 1,300 ohms times the 2 nanofarads. This would be E to the minus, and how much time did they want? 9 microseconds. So 9 microseconds here over this 1,300 2 times 10 to the negative 9. And maybe I should pay close attention to my units. We did this before, but maybe it's worth looking at again. What is an ohm times a farad? Comes out to be seconds, right? An ohm is a volt per amp. A farad is a coulomb per volt. Volts cancel off. Got coulombs. An amp is a coulomb per second. Coulombs cancel off, and you do end up with seconds, which is good because in my exponent, seconds and seconds is going to cancel off. In my constant out in front, I'm going to get coulombs per second, and that's what we call an amp, right? And so that's what we're after. Current. How much current? How many amps are flowing in here? And then the number part, I know you know how to do here. This is 9 times 10 to the minus 6 divided by 1,300 divided by 9 times 10 to the minus 9. Then I can go natural log with the negative of that number, which is pretty small. Then I can multiply that by 5.1 times 10 to the negative 6. Divide that by 1,300. Divide that by 2 times 10 to the negative 9. Coming up with 0.062 amps, or if you want to move the decimal around and call it a milliamp, feel free to do that. And so there's my amperage. And so 62 milliamps at that moment. And obviously getting less and less. The other part of this, part C, then says, what is the maximum amount of current? Well, the maximum amount, and here's where the physics comes in first. What's that? Well, isn't this the equation for the current? A decaying exponential. So isn't the maximum amount the number out in front? Right? So there's the maximum amount. And so now, if I put the number in here, 5.1 micro over, I keep doing this 1,300. I probably should have just multiplied that out. It's like the third time I got to do it. I should have just did it once and wrote it on the side there. But that should be the maximum current. So 5.1 times 10 to the negative 6 divided by 1,300 divided by 2 times 10 to the minus 9, coming up to be almost 2 amps. It is 1.96 amps. And again, this is coulombs, and this is an ohm times a farad, which is a second. Coulombs per second is an amp. So about 2 amps is kind of what this starts. So you hook it up, it's 2 amps, and gets less and less and less and less. And what we just did here is all the way down to 62 milliamps after a long period of time. All right. Fair enough? By the way, I should have asked this. Last two chapters seem a little simpler than the stuff we did before. Yeah? Most of you are shaking your head, yeah? Okay, good. Because I told you it would be, and I hope that you didn't feel like I was throwing a curveball at you. The other reason, too, is I hope you feel maybe a little rejuvenated after you do these easier ones, because we're about to do magnetism. And the magnetism can be hard, too. And so we're going to have some tough math here coming up. Yeah?
How does the Q not over the top? How is that the maximum?
Back here in A, you see when I found current by taking the derivative? And I got this equation? This is the number in front of a decaying exponential. So if you have y equals to a times e to the minus x, and you plot it, it starts off at a and it decays, right? It has its most at the beginning, which is a, and then gets less and less and less. So this is the beginning right here. This is the a. I suppose if you don't remember that from your algebra with exponents, you could probably remember from your calculus, you get maximums by taking the derivative, setting it equal to 0, and you could certainly solve it that way. That seemed like a lot of work to get to the answer, but certainly would work. We can maximize the function. Oh, but in that case, you got to be careful because, oh yeah, I just realized, do you always get maximums when the derivative is equal to 0? No, right? You get maximums at 0. That's one option. What are the other two options? Well, you can get minimums within 0 too. Okay, fair enough.
Undefined.
Yeah, you got to be careful on the boundary limits, right? Because if you have a function like this that goes like that, your maximum is on the boundary. There is no place you can set the derivative equal to 0. And that would be an example of that. This boundary would be its maximum where we got started at time equal to 0. And as I heard somebody else said, the other place you got to be careful for is where the derivative is undefined. You can have a function that goes up to that, and have an undefined derivative. So when you look for maximums, you got to, of course, not only look for where the derivative equals to 0 and make sure it's not a minimum there, but you also got to look at the edge of the boundary, and you also got to look where it's not defined. So, and then, like I said, this would be an example of on the boundary. Well, 39 is a really good circuit. If 39 makes sense to you, you probably won't have any troubles this weekend doing with this, because this kind of puts a lot of pieces together, and I think we're going to need that calculator here in a second again. Do another matrix here. Okay, but let's do this circuit, and I would say this is probably the hardest one we've done. It probably looks trivial for you guys who are in circuits and doing a lot of these here. But for those of you who aren't in circuits, I want to set this one up. And we're going to use a bit of physics here to solve this one, because they're not going to ask everything about it. But I think you'll see here, we've got three batteries. 3 batteries, 3 resistors, and 1 capacitor. Right? It looks like it's got 3 loops, a left, a right, and a middle loop, which you might call 4 branches coming down the middle, if you will. Okay? But let's read the problem here. It says the circuit shown in the figure has been connected for several seconds. Wonder what they're telling me there. Too lazy to do anything quick?
The current through the capacitor is 0.
Yeah, there was something real important there. What was that several seconds really saying?
Very long time.
Yeah, so what does it have to do related to this circuit? Do you guys see it? Yeah, do you see how this capacitor is going to be building up a charge on it? And it may take a little while. You saw some of the numbers I just worked with. It may take a few milliseconds. Even that's probably long. A few microseconds. But certainly after several seconds, what are you going to say about that capacitor? Yeah, enough charge has built up on it that it essentially has whatever voltage is needed to now stop more current from flowing on. And that's going to make this problem a lot easier, because what are you going to say about this branch over here? What's the current over here? 0. Right? Nothing, you know, no fancy unknown current number 4 or 5 over here on the side. It's just 0 current. That capacitor is fully charged. And that's what I wanted you to see in here, or at least one of many things here. But it says, I'll read it again. The circuit in figure 39 has been connected for several seconds. Find the current in the 4-volt battery, B in the 3 ohm resistor, C in the 8-volt battery, D the 3-volt battery, and E find the charge on the capacitor. All right, so they really are saying, look, find the current everywhere, right? Yeah. And so maybe I'll just explain it that way. Let's just find the current everywhere, including where the capacitor is, and then including what the charge on the capacitor is. Okay? But here's really that first key step. I'll say it again. What do we know about this capacitor? It has built up enough charge until what current is over here? 0. And I guess the diagram here gives it away here. After a long period of time, that current is 0. So if I were to put a picture so I can draw on it here and put the capacitor over here and take a look at that 3, is that a 3 over there? The 3-volt battery, and loop it around here with an 8-volt battery, and that being the loop on the far left here, then if I look at just this loop alone, I can really answer E already, can I? What is E saying? He's asking for what is the charge on the capacitor, right? Can you kind of see that this battery is going to be shooting current up this way? Now, it may branch over to that way. We'll talk about it. But I think it's going to branch over to this way and branch over to that way, isn't it? Okay. So if I add up around the loop, if I start here and I realize that this capacitor is going to build up a charge, say, to there, right? Then as I start here and go across, that's a plus 8. As I go across here, it's a plus 3. As I go across the capacitor, it is a negative. Right? I'm going from the higher potential, the pluses, down to the lower one. And that would be Q over C. And that has to equal what? 0. So I know there's a lot of other things going on in this circuit, and that's why it's a fun circuit to do, but just this part of it is pretty simple. It's just 2 batteries in series with each other, the 8-volt and the 3-volt. Added together is 11 volts. This equation is simply saying that there is 11 volts on our capacitance. And so if we know the capacitance, which I thought we read here, oh, it's in the diagram, 6 microfarads. 6 microfarads. And this is 11 volts. 6 times 11 is 66. Volt times a farad is a coulomb. And so there is step E. What is the charge on the capacitor? And I don't know if it's best to solve that one first, but I think it really is important you realize that there is no charge flowing through that, right? All right, well, if I keep going with this, then maybe that might help me simplify things. Let's see, is anything in series or in parallel? As I look at kind of the rest of this, I'm going to have to add to my drawing here. But I now have this capacitor that we've just argued is charged up to 11 volts. Let's keep adding to this circuit. And it looks like the current would go through that. Oh, wait, there's not a top one up there. Would go across here, which your author is calling number 1, and he calls it in that direction. And I kind of like that. It kind of makes sense. As I study the rest of the circuit, I'm kind of looking at this going, all right, this battery is tending to send current that way. Also that way. And it did for a while until the capacitor got full, but after several seconds, it's not sending current that way anymore. So whatever it was, it is now stopped. So the current has been changing here. But after a long period of time, the current is just going this way, which your author calls current number 1. Okay, that seems to make sense. So I like the direction he picks here. It also helps me down here. Doesn't that mean this is current number 1? I mean, if current number 1 comes out of this battery and nothing is going over here, it's like that part of the loop is gone. So the reason I wanted to redraw it here is I just kind of want to disconnect it there. Realizing then that if that upper one is current number 1, then this lower one is also current number 1. And so what's going through this 5 ohm resistance is current number 1. And then also, jumping over to this side here, your author says, all right, let's look at this battery. There is a 4-volt battery. That by itself, I would say, hey, it wants to push current this way. Fair enough? And so again, looking at his direction, I like that. It does look to me like it is going this direction here. And so if he wants to go ahead and call this current number 3, I'm good with that too. That kind of makes sense. It's pushing that way. And if you're going to call that number 3, then you're also required to call that one number 3. Fair enough? Because there would, again, be no place for the current to go. If whatever goes through there goes to the battery, goes through there, there are no nodes along there, right? And so current 3 up there, current 3 down there. And I like those directions. I guess what I don't like is the middle one. Look at that middle one. I think he's taken a wrong choice with that one. He called number 2 up. And since he did, I will also, but I don't know. This is 8 volts. And when it gets here, actually, look, there's no reason to lose any voltage. So isn't that going to be an 8 still? Well, relative to this, so we don't really know exactly what that voltage is. But it's got to go, well, down here. So it can't be more than 4. It's got to go down. But nonetheless, maybe this is a good example to say, let's not worry about the direction. Let's just pick a direction and write out the equations and see what we get, positive or negative. All right, so doing this circuit, I do want you to see, isn't it a lot simpler now that we've taken this part off? And that was an important and useful step here. Separating this off, realizing it's already charged, solving for number E here and finding out what the charge is. And then answering the question of the current in that part of the loop. The current in this part of the loop is 0. So we can just quickly say, okay, there's no current in that part of the loop. And now we can say that I have 3 unknowns. Current 1, current 2, current 3. I need 3 equations. If you look at your loops, we can do a left and a right. Let's see, I put a 5 here. What's the other ones? This is a 3 ohm here, and this is a 5 ohm up there. And so as I write these out, I would say something to this effect. Maybe I'll start here and go across to that battery. So there is a +8. I will then go through here, which is a 3I2, and I'm going against the current. So it is a change of voltage, that is a plus. I would then get here, which is a 5I1 going with the current, and that's a 0. So that would be one of the 3 independent equations I need. I know I can get 2 independent ones because I've got 2 small loops. The question kind of remains is, should I do the 2 small ones or should I include the big one? I'll do the 2 small ones since, like I said, it's probably the way to explain it in terms of making sure you get the independent one. So I'm going to do this loop. Again, maybe I'll start here and go across that way. So this becomes a +4. This becomes a 3I2. I'm going with the current, so it's a minus. This then becomes 5I3 with the current equals a 0. And so there's my 2 of my 3 equations. And I can't get any more independent ones because I've done 2, and that's how many small loops I have. Whether I actually do small loops or not doesn't matter, but if I do 2, it's all I can do for independent ones. So the third equation obviously must come from a node, and there's the node, which gives me the same answer as that node. That's why I don't want to do both nodes. But this node here would say that the current flowing in, I1, is equal, I1 and I2 in that picture. I1 and I2 are flowing in. That has to equal the current flowing out, I3. If I write this in a matrix form, this first equation would become a 1, a 1, a -1 equals 0. This equation up here would become -5 plus 3, 0, -8. This equation here would become 0, -3, -5, -4. Enter them into the calculator, get an answer. So, give you a chance to do this one a second time and show you the calculator again. Oops, I gotta turn it on. I guess I need a 3 by 4 matrix, which I think is what I had before, right? 3 by 4, good. And so I don't need to change any of that. Probably need to change my numbers a lot though. What do I have there? A 1, which is the same as I have. 1, 1, -1, 0. Okay. So there's my first row. -5, -5, enter. Was it 3? 0, 0, -8. All right, teamwork here. All right, the next one. 0, -3, -5, -4. Yay, all right. So there's my matrix A. So if I do the same thing, which I will just hit re-enter, I'll do the RRE. Well, that doesn't really show you how to use a calculator. Maybe that's not a good thing. All right. Clear. Clear. So if I go back to my matrix and the mathematics menu and scroll down the mathematics window till I get to RREF, I can go RREF, reduced row echelon form of matrix. What matrix? Matrix A. And now hit enter. It will give it to me. And, not a surprise, current number 2 comes out to be a negative number. Sure. Oh, and warning, scroll across to make sure it doesn't say times 10 to something. But with these numbers, it shouldn't. So, wouldn't be surprised to see it say something like that. Okay. But again, that's why I thought I'd lay this one out. I like that one in terms of it. Excuse me. That had that extra piece. I reduced it down quite a bit by solving that fact of the long-term current, and that's all they asked about. They could have done the short-term one. That would have set up another system of equations. It would have a system of differential equations, so we don't usually do that to you this semester. We'll wait till next semester for that. So, but that would be more appropriate, at a higher level, and it will be. Some of you will take that. Others of you will do mechanical engineering, so I suppose you won't. But others of you, many of you, will go into some kind of electrical stuff along the way. Well, let me do one more. Tempted to stop because I wanted to move on to magnetism, but I think this is a good one to see. It's well worth. Oh, should I not do another one? Anybody care? Do it. No. I think it is good to see this. Look at 61. 61's got a neat little feature. It's not a real long problem, but 61 does have what I would call the higher ones, or the more complicated ones, when you have resistors and capacitors. Okay? And so you're going to be asked to do a lot of these. This one is not hooked up for a long period of time, although it's a little bit of both. So look closely at that circuit. Study it there for a second. It does have a couple of resistors. How many? 3? 1, 2, 3 resistors. It has a 9-volt battery. It's got a switch and 1 capacitor. And I think you're getting to see the point of this, at least I hope you are, that you have the skills for any combination now, right? So I could put like 17 resistors and 18. No, I won't do that. That's not the point, is to get too much mathematical and have a 18 by 19 matrix. That's not really what we're after here. But what we're after is, now that you understand the basic operations of a capacitor and the basic idea of a resistor and the basic idea of voltage and Ohm's law and conservation of energy and conservation of charge, we should be able to write out any combination and then solve it. Okay? Maybe a lot of math to solve, maybe a differential equation to solve, but that's the fundamental physics. In fact, can't resist. What does it say on the top of your syllabus? The top of all your tests? Physics is about knowing how to apply a few powerful fundamental concepts to explain a universal phenomenon. So we do the basics. We say, look, what is an electric field? Oh, that leads to a capacitor. How does a capacitor work? Oh, Ohm's law, how does that work? Oh, great, put it all together. Now you have 1,900 resistors and 3,000 capacitors. Solve it, you know? Yeah, and obviously at that point now, something that big becomes, part of it becomes mathematical techniques here. But really that's kind of what I have here. And so now that you've got a chance to look at that circuit pretty good, let's read what it says here in 31. It says, look at figure 61. Suppose that the switch has been closed for a time interval significantly long so that the capacitor is now fully charged. Okay, now I know in the picture they show the switch open. All right, but they're saying at this moment, close it. Close it all the way and think about what's going to happen. So let me pause there. Close it for a long period of time. What's going to happen? Okay, so current's going to flow out here. It's going to come along here and then split here. It's going to go, some's going to go there and some's going to go here, right? It's going to start to charge up that capacitor. After a long period of time, what's going to happen to this branch? Yeah, it's going to fill up completely with charge. And the voltage will be on the capacitor will be 9, right? Because again, we know that eventually, oh, no, I apologize. I was thinking it was on that side. No, so it's not going to be 9. It's going to be less than 9. Yeah, no, my mistake there. So it's going to be less than that. In fact, that's why I chose the problem. I did want you to have a little harder one to deal with. Had the resistor been here where I was thinking, it would have been too easy. Okay, but put here, what you're going to have then is you're going to have a voltage here that is less than 9. Because as the switch is closed, the current is still flowing through here. Right? And there is a loss or a drop of voltage here. So the voltage from here to here now becomes the same as the voltage from here to here. And since this one doesn't have any current in here, we could say that there is no voltage change on this resistor after a long period of time. And hence, then, the voltage here is the same as the voltage on that 15. And that's going to be the key to the problem, to realize it's not 9, it is less, it is a fraction of the 9. If I can use another fancy word, I think last time I used current divider. What shall I call this? A voltage divider, because what I have done with these two resistors is I have said that that whole 9 volts is now separated over those two resistors. The total is 9. And so this may come out to be, this is a little more than that one. So for the sake of argument, I don't know what the number is going to come out to be. We'll see that in a second. But this may be 5 volts and that may be 9 volts. But the point is, this would be dividing the voltage. This would be less than that. And of course, the numbers will allow us to go through and figure out how much is that voltage divided by, how much is it cut by.
Why is the voltage on the capacitor the same as the voltage across the 15K? Would it be divided between the capacitor and the 3K?
After a long period of time, there's no current in the 3K ohm. If there's no current, how much voltage change do you have on the 3K? The voltage change on this one is current times resistance. If you have no current here, how much voltage change do you get here? 0. So the voltage, I think what you said is right. You said the voltage here plus here should be the same as the voltage here to here. That's what you said.
Right.
And then we take it one step further. Okay, the voltage change here is 0 because there's no more current flowing. And so it's this plus 0 has to be the same as this. So that and that have to be the same.
So you're saying that the capacitor has voltage just by having no current, but the resistor doesn't?
Yes. Oh, yes. Remember, the resistor has voltage because the current is flowing through there, Ohm's law. The capacitor has voltage because charges have built up on it. So if I was just looking at that last part of the loop and kind of looking at what is happening, current would be coming on here, okay? As we already said, this is going to divide the 9 volts. I'm not sure how much, but for the sake of your question, let me say this is 5 volts, okay? Which is terrible to say because the current is going to vary here, and so it's not always 5 volts. But what I'm trying to say is at first, there's no charge on here, so all 5 volts is here. Then as time goes along, this might have 1 volt, so this has 4. This has 2, this has 3. Eventually this builds up to 5, and that goes down to 0.
So we're saying while the switch is open, or while the switch is closed?
Oh, I'm talking about when the switch is closed.
Okay.
So the first part of it is why the switch is closed for a long period of time.
Okay,
Oh, right. Okay, yeah. Now there's more to the problem, but let me come back here and say, yeah, this is just the first part, the first sentence. It says, suppose the switch has been closed for a long time interval. Okay.
So you're saying while the switch is closed?
So while the switch is closed. Okay. What's going to happen is current is going to continue to go through here, like that. And at first it'll flow onto here, but after a period of time that will get full, nothing more will be flowing over here, and that's why I would say there's no voltage here across this one anymore. And then this one's got the same voltage as that one, which I think is what I'm going to need to move forward with this problem. I haven't even got to the question yet, but I think I'm going to need how much charge is on that capacitor and how much voltage is on that capacitor before I open the switch. Because that's the next part of the question. The next part of the question then says, find A, the steady state current in each resistor, B, the charge Q on the capacitor, and there it is. Now C, open the switch and call this time equals to 0. Write an equation for the current in resistor number 2, which is the 15 kiloohms, as a function of time. And then D, find the time interval required for the charged capacitor to drop down to 1/5 of its initial value. So the first two, A and B, are with the switch closed. But then C and D are saying, what's going to happen now when you open it, right? And I think you would agree, we haven't done anything like this, except this doghouse we're building. I have shown you how to use a hammer and a nail and a saw. And so now let's build the doghouse, right? You have all the pieces, put them together, right? That's what makes the homework, the test, a bit harder. You got to put together the individual pieces here. Something you haven't seen before here. All right, so let's start with the switch closed. In fact, why don't I draw a little nicer picture with the switch closed and continue that conversation that we got started with here. So here is the 9-volt battery with the switch in the closed position. This 12 kilo ohm resistor has current that is going to split off and go through the 15 kilo ohm, but also split off and go to this far right branch. And this far right branch has a 10 and a 3, a 10 microfarad capacitor and a 3 kilo ohm resistor. Fair enough? And if we labeled these in terms of current, we might say something like this. We might say, all right, call this current number 1. As it flows along, it hits this node. From that node, some of it goes down, current number 2, and some of it goes through this branch with the capacitor, call it number 3. But they were really kind of nice to us here at the beginning. They did say after a long period of time. So if I put as time goes to infinity, current number 3 goes to 0. All right, that was our discussion. This one's pretty dry too. Let's see if I can do a better one here. All right, and so that was our discussion. Now, what does that mean about current number 1? What does current number 1 approach? Yeah, it's I2. Do you see that after a long period of time? And that, like I said, is really kind of the trick to these first two steps, A and B, is to realize that that one is kind of out of the loop. Everything's just going like this. Really, all we have is a voltage battery, 9 volts, with 2 resistors in series. Very simple circuit at that point. So current number 1 approaches current number 2. And I can even find that by writing down the equivalent resistance. This is 9 volts, and then this is the equivalent of 2 in series. A 15 and a 12 makes a 27 kilo ohm resistor in series. And so that's what I would say this circuit looks like after the switch is closed for a long period of time. There is no current in that far right branch, and there is an equivalent resistance of the 12 and the 15. And the reason that's helpful is, of course, that gives me that current. And so the current here, that is current number 1 equaling current number 2, does equal then 9 volts divided by 27,000. I guess 9 divided by 27 is a third, and a 1 divided by a kilo is a milli, and so I have a third of a milliamp, right? That sounds kind of funny, huh? Kilo divided by kilo is a milli? That's weird. Oh, anyways, but did that make sense, or should I write out all the numbers? Right? All right, so that's what the kilo means. Take you all the way back to chapter 1, your unit conversion, right? 1 over 1,000 is a milli. So there's my milli, there's my amp, there's my 1/3. All right, so that's what it tells me so far here, is that I've got a third of a milliamp kind of going through this little circuitry. Okay? Now, the question A, and for that matter B, are really with it closed. Let's go back and read it here. It says A, find the steady state current in each resistor. Oh, I guess I did that, right? Each of the resistors, meaning this one and this one, have the same 1/3 of a milliamp, and that one has 0. Okay. B, the charge Q on the capacitor. And that's why I needed you to think a little bit about this, is that while that switch is closed, the fact that you have no current in this side means there's no voltage here. So if we do a little bit of a loop here, we can see, as we add it across here, that the voltage here is going to be equal to the voltage here, because that one's going to be 0. I'll just write it out with Kirchhoff's loop rule, right? This is build up a charge of a bunch of pluses up here and a bunch of negatives down there. And so maybe I will start here and go around the loop. And so if I start here, I will say I have a 15 kilo ohms times a third of a milliamp. That is the voltage change from here to here, and it is a negative. As I continue to go around the loop, I look at the voltage change here. Since we said there was no current there, I would say 0 change. I'm not sure whether I should call it a plus or minus 0, because I'm not going with or against the current, but it doesn't really matter there, so it's a 0. And then I go from here to here, and that's an increase in voltage. It is a plus the voltage on the capacitor. And so that's how I get the voltage on the capacitor. That's why I said the voltage on the capacitor will come out to be the same voltage that is on here, which is not 9, as we'll see here in a moment. It's a fraction of 9, and hence why we call it a voltage divider. And so 15 divided by 3 is 5. Kilo times milli cancels. Ohm times amp is a volt. So the voltage on the capacitor is 5 volts, right? A fraction of it, okay? And so that's how much it builds up to. And a big reason I picked this one is it's so tempting for beginning students to say that that capacitor builds up a charge until it's 9 volts. And that's really what I wanted you to see. It does not build up to 9 volts, the way those resistors are set up there, right? Depending on how the resistors are arranged, it could have been some other crazy combination. Well, once I have that, then I can get the charge, because capacitance equals the charge over the voltage, meaning the charge is capacitance times the voltage. The capacitance is 10 microfarads. The voltage is 5 volts. 10 times a 5 is a 50. 50, there's the micro, and a farad is a coulomb per volt. So there is A and B. What is the voltage? What is the charge? Okay? And obviously if you know one, you know the other. So the real trick is finding either the voltage or the charge, and that leads you to the other one. And in this case, the real trick was to realize that there'd be no current in that far loop after a long period of time, and then we can then get the current in here, and from that we can do this second loop and get it. So again, notice I just used Kirchhoff's loop rule. Do the voltages, whatever math you get, solve the math. If it happens to be a differential equation, so be it. Solve the differential equation. If it happens to be 3 unknowns and coupled unknowns, then you have to do kind of the matrix. If they're this one where they're not coupled, it's kind of nice. You can kind of do it piece by piece. Get the total current. The total current gives you the partial voltage. The partial voltage gives you the voltage on the capacitor, and you get the charge. Okay? So sometimes the math lays itself out easy. Sometimes it lays it out hard. We just have to deal with whatever the problem brings in hand. All right, but now I think it gets a little more interesting where we do this. Now, the switch is now opened. So call this time equals to 0. Write the equation for the current in resistor number 2 as a function of time. All right, so knowing these initial conditions, and let me put them over here. So this capacitor has a voltage of 5 volts. It's got a charge of 50 microcoulombs on it already. And now we're going to go ahead and open that circuit. So I'll change my picture. I will open that. I will then sort of erase all this. And they say, go ahead and call this time equals to 0. And fortunately, this really is no different than what we've already done, but that's my point of choosing this problem. Do you see? it is no different than we've already done. I mean, think about now when we open this. What would you say about this part of the loop over here, this part of this branch over here on this left root? There's no current, right? This has been opened. You could think of this as then completely being separated off, right? So this isn't happening. This resistor, you know, there's no current through there. There's no voltage. This battery's not doing any good. And so what do you notice here? Don't we just have a charged capacitor that is discharging? Now in this case it discharges through 2 resistors. When we wrote out the equation, we said the current, well, I should do charge first. But when we did charge as a function of time, we said it was the initial charge times e to the minus t over tau. But let's come back and look at how did we get tau? Wasn't tau the capacitor and the resistor? And of course what's changed now is we have 2, but can you see how those 2 can be equivalent to 1? Can you see they're in series? Yeah, so this should come out to be 50 microcoulombs times e to the minus t over RC, where RC now is 10 microfarads for the C, but the R is the 2 of them in series. And so we've got a 15 and a 3, which make 18 kiloohms there. And so there is my equation. What's this? 10 times 18 is 180. Oh, a micro and a kilo makes a milli. All right. So there is my equation for the charge. Now, I better come back here because I don't think they asked for charge. Didn't they ask for current? Yeah, C says, the switch is now opened. Write down the equation for the current as a function of time. D does say, find the time interval for which the charge on the capacitor is reduced to 1/5 of its value. Well, in the interest of time, so we can start magnetism, I'll do D over here by saying 1/5 of 50 microcoulombs equals 50 microcoulombs e to the minus t over 180 milliseconds there, right? And so you can solve that and get time.
Could you also do this by solving for the initial current and saying I of C is equal to I initial times V?
Say that again?
Solve for the initial current.
Okay. And then what are you going to do with that?
And then you say that I of t is equal to the initial current times e to the negative t over tau.
Sure. And now I would ask how you got this.
How did I get I?
How'd you get that equation?
From circuits.
Okay, fair enough. Not exactly what I was looking for, though. Because what I was going to say is, isn't that the derivative of this?
Yeah.
So this is the one we derived in class. There's no point in also deriving this unless you want to, okay? But take the derivative of that to get this. So, but we also, I should emphasize, did this about an hour ago. We did take the derivative of that. So I was wondering why I'm asking you, were you going to say, well, we did it an hour ago? Or were you going to say, I did it in circuits? Okay, so, but this is the derivative of that. So, since we worked out that, I jumped to D first because it asked for the charge and that was our basic equation. But I can jump back to C now, take that, take its derivative, which would give me this, which then would...
Is that true for every capacitor in every circuit?
Well, I'll say no. What it is, though, is it would have to be the equivalent capacitance and the equivalent resistance. So if I had something that looked like this, okay, and I charge those two capacitors up, and it goes to discharge, I could replace that with the equivalent capacitance there and the equivalent resistance there, and then that equation would be valid. So as long as I have a circuit that could be reduced down to equivalent 1 capacitor and equivalent 1 resistor, which that more complicated one can be, but not all can, then I can just apply that equation. So it's one of these things where it's a great equation, but you got to remember its limitations, otherwise you'll be tempted to use it in the wrong place.
You just have to solve for it.
Yeah, which is why we do, and hopefully your education takes you both places. In the science class here, we give you the fundamentals to say, look, if you don't really know if the equation is valid, or if you never can't find an equation that's valid, or never anybody has done it before, you do it. Just write out the equation and solve it, which, sounds so easy. Write out the equation. That's hard in itself. Solve it. Nobody maybe has done it before because it's not that easy. But that's the fundamental physics. Now you take that then over into your circuits class, then you'll learn, special cases. Let's use this for this case. Let's use this for this case. Let's use this for this case. And so it gives you a way of solving some pretty complicated problems pretty quickly. But I think my job in the science class is to remember, when you're over in the engineering class, to remember that if you forget where these things are derived from, it's like forgetting what the first floor is made out of and deciding to put a pool on the second story. Well, we only made the first story out of balsa wood. You're going to run into troubles. You can do all the things about the pool and the design just fine, but if the stuff below it, where it comes from, is not appropriate, it doesn't work right. So you need to remember both, which is why you take a science class and an engineering class, right? And that's your education. All right, well, with all that said then, why don't I, in the short time we have left, go into magnetism and start off with a little bit of comment here. We're a little bit behind on the syllabus. I don't think it will be wise to rush through this magnetism and have the test on schedule. So I'm thinking your test being scheduled on November 1 is probably best on that next Tuesday, whatever that comes out to be, the 6th, I believe, there. If you take 1 and add 5. For other reasons, too. I heard a lot of you have big math tests that week. And some others of you told me you have a big Halloween night, so there's no way you can do the first and do successful with it. So, for a lot of reasons, we're going to do that. And there is one other. I'm going to have to confirm this with Don a little bit. But if everything falls into place, I might make sure that day is a good day where example problems are done. And I might leave that in Don's hand. My oldest son is a senior, and he wants to go travel down to San Diego, and there's about 4 colleges. And I go, that might be a good time. So maybe I'll take the Thursday, Friday, and go see UCSB and San Diego State. And there's 2 private schools down there, and go to that. So I'll let you know more about that, but I may not be here, and we'll check it out. Colleges. Honest, it's not the Chargers game I'm going to. But, as long as you're down. No. Actually, I did look up. They're playing Kansas City, but I forgot to look to see if they're playing at home or not. Anybody know? No? Chargers fans? All right. So maybe when we get an LA team back here, we can stop working for the Chargers. Bring the Rams back, huh? All right, bring the Rams back. Although, I was thinking about that. I think the Chargers are going to put a hard bid to come up here.
They approved the stadium about
a
month ago.
Yeah.
To be built.
Yeah.
They just need the team.
Yeah, they got to get at least one commitment, and they're building it big enough for 2 teams. It'd be weird if LA goes from no teams to 2 teams. But I think the Chargers, because half their fan base is in the LA area, and so they'll lose like half their fans. Or if they move up from San Diego, then all the San Diego fans will come to LA instead of the LA ones. So they'll have more fans. But maybe I'm wrong there. But I think that would be a wise business move. But the Rams, you're right, would be better. Yeah, they should have never left LA. All right. So let's jump into chapter 29. And just the short amount of time we have left. So I'll just give you the basics, which is probably a good approach, because as we shift gears here, and we get into magnetism.
Playing in San Diego.
They are playing in San Diego? Oh, great. I better get a hotel room quick. All right.
Sunday night, though. The night game.
Oh, it's not Thursday?
Oh, no, Thursday night game.
Yeah, it is that Thursday the 1st, right? Yeah, night game, right? So I can see the colleges in the day. All right, all right. All right, so chapter 29 is magnetic fields. All right. And let me just start simply with this. Nothing real complicated. We'll just start off with vocabulary here. Terminology here. Just some simple observations. Take you all the way back to kind of the beginning of these whole magnets. I got a bunch up here. Obviously not enough we're going to get here to today. But you may recognize a compass. Okay? And one of the first uses of magnetism was a very interesting property. Without explaining the property, it was observed that you take some magnetic material, some iron material here. I think the ancient Chinese were using, I think it's on the rock. Magnetite, thank you. Yeah, magnetite. But they noticed an interesting part of it. And I don't know if you can see, we don't have a, I don't think high enough stadiums to see it. But can you see this thing move around? And one end of it points towards the north. Okay? And so maybe if I tilt it a little bit that way, if I were to, just give it a little nudge and it'll kind of rotate around. But this one, this edge, or this pointer, which is painted a little bit darker than that side, so you can kind of tell the difference. This is kind of a blue side. This is kind of a silver side. I'll kind of stop it a little bit from rocking. But as if it can freely move around, it will have a tendency for one end to be angled towards the north and another end to be angled towards the south. So, doesn't surprise you then, as we go to name the parts of a magnet, that we start here. We start here and simply say that all magnets then are going to have part of it that points to the north. So we will call the edge of the magnet, or the point of the magnet that points to the north, a north-seeking pole. Kind of makes sense? Because the other end is pointing which way? To the south. So the other end of the magnet, we will give the term a south-seeking pole. I must admit, we get a little lazy and call the north-seeking pole a north pole and the south-seeking pole a south pole. But please, we never really mean a geographical North Pole. This is not where Santa lives. He's not on the magnet. Santa's up there at the North Pole, okay? But that can lead to some confusion when we talk about a magnet and a compass in relationship to the Earth. Are we talking about the North Pole of the magnet, north-seeking side of the magnet, or are we talking about the geographical North Pole? It gets even worse because, as we will soon discover here, the compass doesn't exactly go to the perfect geographic North Pole. So we will have a magnetic geographic North Pole. Okay, and so the names can get a little confusing. So I'll try, especially at the beginning, to always say one side points towards the north. We call that the north-seeking pole, south-seeking pole.
I thought that the north-seeking pole of a compass was its south pole. Why do you have a middle as north pole?
No, the side that seeks or points to the north is called a North Pole. That's why it's called a North Pole, because the ancients looked at it and they say, oh, this one goes to the north. We'll call that the north side.
Seeks the geographic north.
Seeks the geographic north? Is that what you mean? Hold off on your question. I think I know what you might be getting at.
Geographic north.
Yeah.
Earth is the Earth's south pole.
Yeah.
That's what you're getting.
I think that's what you're getting at.
Yeah.
Let me take a next step here, step 2 here, okay? But there's step 1. And so if I ever draw a magnet, I'm going to draw it this way. This is what you're going to see in the book. This is what you're going to see in the next chapter. We're going to take a piece of metal or some kind of material and say it's magnetic. And on one end we will put a little N, and the other end we will put a little S, right? What do we mean by that? The north side and the south side. In fact, probably can't see it, but the ones you are going to play with in lab look like this. This one shows up a little better, so maybe I'll grab it. But here's my bar magnet. Can you see a little engraved on this side that says N? That's the North Pole. North seeking pole, right? What's this? South seeking pole here. Here's where it gets interesting. What if I break this in half? Not that I can break this one in half, but if I cut it in half, what would I get then? Would I get a pole north, pole south, and I would have what you might call an individual pole, a monopole? No. And what ends up happening then is you end up having two magnets. You end up having still a smaller magnet, two of them, one side seeking the north and the other side seeking the south. And so what we like to say is all magnets, and again, no explanation yet. We're not going to have time to really explain any of the physics. It's more about the terminology that we can talk about it here. But at this point, this is just vocabulary, the vernacular here. We got a north-seeking pole and we got a south-seeking pole. It's why we say all magnets have two poles. It's why we say never have we found by itself a single one, what we would call a monopole. Now, that's not to say somebody won't find them. I can think of many experiments that I watched happen when I was at UCLA, and the millions, if not hundreds of millions of dollars that were spent going up to Alaska and areas trying to discover and find, does the world have any monopoles? And of date, we have never found any. So maybe there's more to be found. I for one, am fairly convinced for other reasons that monopoles don't exist, but that doesn't mean I don't think we shouldn't keep looking to see if the science is a little different than we think. So you'll hear the author talk about that. But here's what then is you want to be careful with in terms of the terminology here. Because as I get into the next observation here, step 2, if I take two magnets and I hold them together, let's say I take a magnet and another magnet, and I bring them close together. The arrangement of how I can bring them together gives me 4 possibilities. What will happen here? Well, let's see. So the reason we have this little boat and this bar magnet is so that I can put the boat over here. I can put the magnet in here. I happen to know north is about that way, so I'm going to put the little boat east and west. It probably wants to turn or seek to the north. It can't right now because there's friction. Fair enough? So what if I add a little water to my boat, or to my pan until the boat floats, and significantly reduce the friction? You can see it turning, right? And obviously there's a lot of interesting physics there, which again we'll have to do more on, what's today, Thursday, so Tuesday. But didn't one side seek the north? Okay, so you can see it. Maybe I'll put a little black or red dot on there, okay, which doesn't look very red by the time I put it on there, but that is the north seeking pole. Let me do that for a second one. Let me take this one here and kind of discover which end of this is the north seeking pole. Okay, again, same general wording, right? One side seeks the north. So I'll put a little mark on that one. Not that I'm going to need to pick that one up here, but now this will give me a chance to show you again some more of the basic principles. What do you think might happen if I brought a north pole near a north pole? So, north pole near a north pole, right? They repel. All right. What do you think will happen if I bring a north near a south? All right, so I'll use the south and bring it near that north. Maybe I'll put it off to the side so you can see it attracts, right? What if I bring my south near that south? So here's the south over here. I'll bring it near it. Right? It repels, right? And then what do you think's going to happen here? Well, it's the same thing as there, right? It's just I'm using this is the north one, and this is the south one, which now that I got it spinning, I'll put it back so that you'll know that that is the north-seeking side. But the north here and the south there then attract each other. So what we have, yeah?
So the left and right of that magnet has polarity, but do the faces also have polarity, like the up and down parts?
Ah, good question. Maybe I'll...
Are there rules for how that works?
The whole magnetism is now not on the face. It's through the whole material.
Okay.
So really the face is irrelevant.
Yeah.
It's the material inside. And it's one solid piece. But again, working forward with our terminology, and hopefully getting to your question too here real soon, is that what I would have is I would have these guys pushing apart, and so we have them repelling, right? Whereas these guys here, the opposite poles then attract. These guys here, like poles ends up repelling, and opposite poles end up attracting. And hopefully this doesn't look any different than we saw on the very first day. Didn't we do something like this on the first day? Didn't I come out there with the vinyl and the acetate and I rubbed it and I said we got a positive charge, we got a negative charge. So we really kind of have the same thing where we can say like poles end up repelling. But the opposite poles are what we will call the unlike poles. When they're brought together, they tend to attract. Now, it should make it easy to remember, right? Because this magnetic forces seem to have the same general rule as the electric forces. And I would agree, that does make it easy, almost too easy. Because I see students confusing magnetic forces with electrical forces. I mean, just let me give you an example. I don't know how many times I've told you, and hopefully you won't do this, but the student will pick it up and say, hey, here's my magnet. What's the charge on this side? Charge? This is not electrical, it is magnetic. Okay? And so I'm not talking about the charge on here. This is not charge. This is magnetic. This is something in addition to, right? I wouldn't come over here and say, hey, this magnet falls. Huh. It didn't fall because of the magnetic forces. It fell because of the gravitation. You wouldn't confuse magnet forces with gravity, would you? And so the same thing. We've got gravitational forces, we got electrical forces, and we got magnetic forces. So that's why we do not say like charges here. This says like poles. Okay? And so what you'll see here is the patterns we see and the principles we see for magnetism are very, very close as electricity. And because of that, they're easy to learn, but they're then also easy to confuse and to cross one terminology with the other. So just be careful with that, yeah.
Do they dissipate over time like charges?
I'll say yes and no to that. The no part is on an atomic level, no. But collectively as a group, the reason this one is strong is because all the atoms are in alignment together. And they will tend to, just because of the heat of them and people dropping them on the ground, tend to make the atoms misalign. And once they start misaligning, then they're not acting collectively as a group. Each individual atom is still just as strong. So part of me wants to say you don't lose any magnetism. But the other part is you lose the collective effect of them. So that's why the magnet gets weaker. Yeah.
Where did the work come from that allows that magnet to do work?
Oh, when it was made, it was made by doing work on it, putting it in a magnetic field, heating it up, cooling it down. Yeah. Okay. So this is our magnetic forces. Now, before we leave here, at least let me show you this much. Step number 3 really now starts to at least touch on the physics. So we're going to have to obviously do most of the physics starting next week here. But where does all this magnetism come from? I mean, at this point, I really haven't explained why there is magnets, why there is a force between them. But I would say this, going back to our electrical forces, if I had put a positive charge here and a positive charge here, you would have said those two charges repelled. And if I were to ask you how does the second one know it's supposed to be pushed from the first one, you would say? The electric field, right? The first one carries a field, and it's the field that pushes on the second one, right? So if I were to come over to here and say, how does this magnet here, which I label with a north and south pole, know that it's supposed to be pushed away from there? What would you say about this one? It's creating a magnetic field. Now, I won't have time today to kind of show it to you. Maybe I can roughly give you a picture of it. But here is a very strong magnet, much stronger than those bar magnets. Here, oh, I need a good, can you see the little needles?
There's a bigger one on the...
Oh, yeah, this one, it's not as accurate, but it is easier to see. Can you see that surrounding this is something? And that something is what we were going to call a field. And its shape and its pattern is what we're going to be looking at. And how strongly then would, say, this magnet, say, interact with another magnet? Again, running low on time, but there is obviously an interaction between those magnets. There's obviously an interaction between this strong magnet and this nail. And so I will leave you for the weekend with this statement, that magnetic fields are then coming from or created by what? And this is why we study it second. Moving charges make a magnetic field. Have we been working with moving charges? What have we been called moving charges for the last 2 chapters? Current. So all these problems I did today, all these examples we have been doing for the last 2 weeks, we've had current. And we've talked about the voltage, and we've talked about the resistance. But every time we get current, we also get what? Magnetism. We get magnetic fields. In case you don't believe me, I'll show 2 quick ones real quick and let you go. Here I've got a wire. I've got it in a magnetic field. Right now you will probably see that I have a good size battery connected to a switch, which then goes through a wire. Fair enough? But I would say right now, without this switch being closed, there is no current in here. And because there is no current, there is no magnetism from this one. It's all, I have just one magnet. I have no interaction. But if I were to put current in this one, I claim that this one becomes a magnet also. Because I'm trying to say, where does magnetism come from? Moving charges. So if I touch this switch, in case you missed it, if I touch this switch, I will now have current flowing in here. That's a magnet. That's a magnet. We arranged them so they repelled, and so you clearly saw them jump away. Also, real quickly, you can see it here. If I take a power supply, turn on the, well, okay, power's on. If I take these nails, I get near a nail, it doesn't attract like here because it's off, no current. If I turn it on, oh, that sucks. There we go. That's much better. Turn it off. Turn it on. Turn it off. Right? The magnetism comes from moving charges. If I make something maybe a little more practical here, I can take the electricity and pass it through some wires. In this case, the wires are wrapped around a piece of wood. I'll call this an armature, if you will. I will take a magnet, so this will be my magnet. And unfortunately, this part kind of blocks a lot of your views. Maybe I'll move it back here a little bit. But I have this set of magnets. Right now, the current is off, right? So this is not a magnet. No current is flowing. But this magnetism comes from moving charges. If I turn it on, give it a little help, then I will have an interaction. I will have some forces, or maybe more appropriately a torque here, where the interaction of this, what I'll call an electromagnet, is then interacting with this magnet, and I have an electric motor as I have an interaction of my magnetic fields. So, good stopping point. I'll let you go and do the homework and read the chapter and come back on Tuesday.